Hello, I'm Dr. Deborah Campbell, and this is going to be a video as a companion piece to Patrick J. Hurley's Concise Introduction to Logic, particularly Chapter 6, Propositional Logic, and even more specifically, Section 6.3, Truth Tables Explained. I'm just going to walk you through the rationale for a truth table and the construction of a truth table. Okay, so in 6.1, we learned how to symbolize statements. In 6.2, hopefully you learned how the logical operators preserve the truth functionality in a compound statement, how they function truth functionally. So all of those exercises in 6.2 either assumed you knew the truth value of the statements in the compound statement, so you could then look at the operator and calculate the final value, or they stipulated that certain letters were true and certain letters were false. Again, so that you could then look at how they were logically related and calculate the overall truth value of the compound statement. And remember, all of this is going toward Section 6.4, which is once we learn how to symbolize and calculate truth values for statements, we can then put those together in arguments and check the validity of an argument. Okay, so that's where all of this is headed. What happens, however, when you don't know the truth value of the statements involved in your compound statement or in your argument? For example, take some statements that I just chose. Inflation is on the rise. Is that true or false? Not sure. What about bond prices will decline? Again, not sure the truth value of that. It is the kind of statement that will have a truth value, but let's say we don't know the truth value of the individual statements. Stock prices will go up. Again, not sure if that's true or false. So what happens if you don't know the truth value of the statements? Well, a truth table then can be very helpful because you can figure out, based on how many statements you have in the compound statements and how many operators, you can determine you can still determine something about the truth value of that statement. That is, you can determine if the statement is constructed in such a way that no matter what the truth value of the individual claims, it's just going to be always logically true. That's called a tautology. Or you might be able to show that a statement, no matter what the truth value of the individual claims, the logical construction of the statement is that it will always turn out false. Now, the majority of statements, it depends, and those are called contingent. So let me give you an example and showing you how to construct a truth table to prove that some statements are logically false, some statements are logically true, and some are contingent. Okay, so again, sometimes you can know some things about propositions even without knowing the truth value of the individual claims. And this is called classifying propositions. Part 1 of 6.3, the exercise sets are about constructing tables to classify propositions. For example, I've just made up some examples. If someone were to say I is logically equivalent to not I, they would be saying inflation is on the rise if and only if inflation is not on the rise. You would immediately say, okay, logically that makes no sense. It's because it's a self-contradictory statement. If you remember the truth table from section 6.2 about the logical equivalence, the biconditional, you know that in order for a statement, an equivalence to be true, it has to be the same value on each side. So I can never be equivalent to not I, just logically. This is called a self-contradictory statement. Now, how can we prove this via a truth table? Okay. At the very beginning of 6.3, they give you a little formula, algorithm, for the construction of a truth table to make sure you're testing all the logically combinations of truth and falsity for that statement, for that compound statement. So don't get thrown off by the fact that this is a formula. It's very easy. And if you follow this method very carefully, step by step, it will become fairly automatic. It's a purely mechanical process. But let's make sure we understand the formula. So in order to create a truth table to check, how does this turn out if I is true? How does it turn out if I is false? Again, the truth table checks all the logically possible combinations of truth and falsity for the sentence letters. Well, the number of lines in the table to get all the possible combinations has to be the number 2 to the nth power. 2, because every sentence letter can only be true or false. So it's true to the nth power, where the n is the number of distinct letters in your compound proposition. So we start with this easy one. We only have one letter. So to work out the formula, to make sure we're constructing our truth table correctly, we would say the number of lines in this truth table are going to have to be 2 for true false to the power of 1. That's 2 times 1 equals 2. So we need exactly 2 lines in our truth table, okay? So we just need 2 lines in the truth table, and the next step to make sure you're constructing it correctly is to take the total number of lines in the table and divide that in half. 2 divided by 2 equals 1. Now you might say, well, we're just going backwards. Okay, trust me, as we get to more letters in the table, this will make a lot more sense. To create the table and to make sure you're constructing them the same way every time, you find the total number of lines in the table based on the number of different sentence letters, and then you take that total number, divide in half. 2 divided by 2 is 1, so that means you're going to start with your first letter, and you're going to have 1 true and 1 false. Okay? So again, these are the 2 possibilities. And since that letter is repeated, you go over to where that letter shows up again, and you carry over the same assignment. Okay? So I can only be true or false. It occurs again on this side in terms of not I, so the I is still true, false. Now, you have to take care of that negation in order to calculate the values for these the lines in the table. So if I is true, not I becomes false, and you're done with that value. If you want, if it helps, every time you're finished with a value, you can put a line through it. If I is false, then not I becomes true, right? Because you want the compound value on each side of the equivalence. So true is equivalent false. Well, obviously, remembering how the equivalence works, it's false. And false is equivalent true is also false. So that table demonstrates that no matter what the value of I, this particular proposition can be classified as a self-contradictory statement. Now, obviously, it made sense to us as soon as you said I is equivalent to not I, but this is how you would prove it to somebody. Okay? My second example is I'm looking at a proposition that has 2 distinct sentence letters. Now, you might say, no, there are 3 letters. Remember, the formula is distinct sentence letters. There are only 2 different letters in this table. So how many lines would this table have to be constructed properly to test out how this turns out under the main operator for every possible combination of truth and falsity? So for this particular example, the second example, the number of lines in the table is going to be 2 to the second power, to the power of 2, because they're 2 different letters. 2 to the second, 2 times 2 equals 4. So this will have to be a 4-line table to capture the 4 logical possibilities. And then how do we start constructing the table? You take the total number of lines 4, you divide in half, 4 divided by 2 equals 2, and under the leftmost letter, and always do this the same way, start on the left side, the first letter, and you take 2 true and 2 false. Okay? Now again, in order to make sure you get the combination correctly, following the formula, after you have filled in half true, half false for the total lines under the first letter on the left, then you go to the next different letter and you divide in half again. 2 divided in half, 2 divided by 2 is 1. So the second letter will have true, false, true, false. Okay? When that letter is repeated, you give it the same assignments. So this other B would also have true, false, true, false. Okay? Now, how do you go about filling out the rest of the table to see how this proposition turns out under the main operator? Well, you follow the same order of operations. You would take in parentheses, and you would calculate, remember, for a dot, true and true is true, true and false is false, false and true is false, false and false is false. Now again, when you're finished with certain values, you can draw a line through those if it makes it easier to follow. Now you calculate your main operator. True implies true. Now remember, you're switching operators. For the implication or horseshoe, true implies true is true. False implies false is also true, right? False implies true, also true. False implies false, also true. Oh, what happened? Well, no matter what the values of A and B were, and we tried all 4 possible combinations, it comes out true every time. This is called a tautology. Okay? Again, we could know that if A and B are true, then they imply B. Actually, even saying that, you might recall that if you said A and B are true, then B follows, because for a conjunction to be true, each conjunct has to be true. So the fact that A and B implies B, that's a tautology. Okay? My third and final example is, what if you have 3 distinct letters? Okay? Again, go back to your formula. The number of lines in the table, okay, is going to be 2 to the 3rd, right, for 3 distinct sentence letters. And so you take 2 times 2 times 2, that's going to be 8, is going to be the total lines. Take the total number of lines and divide in half, and you're going to start with 4 true and 4 false under the first letter. Okay? So it would be 4 true, 4 false. Okay? You go to the next letter, divide in half again. Again, follow the exact same method every time. You go to the next letter, 4 divided by in half, 4 divided by 2 is 2. So the B will have trues and falses by 2s all the way down for each line. Okay? And you get to the third and final letter, 2 divided by 2 is 1. When you get to your final letter, if you've done it correctly, it should always be alternating trues and falses all the way down. Okay? So, lo and behold, the algorithm works out beautifully that if you have 3 distinct letters, you need 8 total lines. If you start with the first letter, 4 and 4, then by 2s, and then every other one. Then you go about calculating this, and again, here's the main operator. You would go about calculating the wedge and then the horseshoe. All right? In this case, and I'll just go through it quickly, it's a wedge, remember? So true or true is true, true. You only need one to be true for the whole thing to be true, but when you get to the last 2 lines, it would be false. And then the horseshoe, always remember to keep your mind on which operator and what the rule is. It's only going to be false when you have a true implies false. So first line's going to be true. This line will be false. Now, as soon as you have 1 true and 1 false, it can no longer be classified as self-contradictory or tautology. This, you wouldn't even have to fill the rest of it out. It's going to be contingent. Under the main operator, if you have at least 1 true and 1 false, it's a contingent proposition. Okay, what's the other part of 6.3, part 2? Oh, and I should say one other thing. Just follow the formula. The longest truth tables you have to do in the exercises is, I believe, you have 4 distinct sentence letters. So 2 to the 4th would be 2 times 2 times 2 times 2, which would be 16 lines. So it would be, for 4 letters, it would be 8 true, 8 false, and then by 4s, and then by 2s, and then every other one. So I think there is in the homework maybe 1 or 2 16-line truth tables. Again, they just want you to practice the method. Okay, so that's constructing a truth table. The other part of 6.3, part 2, is about comparing propositions. So once you know how to construct a truth table for a single proposition, you can classify it as either always false, self-contradictory, always true, a tautology, or sometimes true, sometimes false, that's contingent. But what about when you compare propositions? Well, you construct the truth table the same way for each proposition. There's just one thing to keep in mind. Okay, these 2 propositions that you're comparing, they each have 2 sentence letters, the same 2 letters. And so you would start with your leftmost table. You have 2 distinct letters. It's going to be a 4-line table. So you're going to start true, true, false, false, and then B will be true, false, true, false. But here's the thing to remember. When you go to your next table, you don't start over again putting true, true, false, false under the B. What you do instead is, if you're going to compare, you have to copy over the same values from the first table into under the letters for the second. So the assignment in this table, the assignment to B was alternating true, false, true, false. So in order to compare them, you have to put true, false under the B, and then true, true, false, false under the A. That's the only thing you need to remember about comparing propositions. So that's truth tables explained fairly quickly. Again, plenty of examples in the book. You can always email me if you have other questions, and I hope that was helpful.